Okay. So binding energy, that means the amount of energy released, right? When these protons. Okay, so my question was, yeah, let's join. When energy is high, stability is low. So everyone is okay with that. When energy released, when energy released is high, then what can we tell about the stability? Stability is high. Why? Energy released means initially it has a lot of energy, and when it is releasing energy, its energy will reduce. So it's actually less energy, high stability, right? So okay with this point, the second one. Can you just raise hand if you are clear with this second point? Sajay and Shama, okay. Now, what is this binding energy? Binding energy, that is the energy released when these protons and neutrons combine, right? And to make this not only helium, here I'm using the example for helium. When these two combine, it releases certain amount of energy. That energy we call as the binding energy. So, compare, if this energy released is high, then energy in the nucleus is low. That means this nucleus will become more stable. It becomes more stable when binding energy released is high. So do you agree, if binding energy is high, then stability is high? Binding energy per nucleon, okay? So now let me know. Are you all clear? If binding energy per nucleon is high, stability is high. So coming back to this question, which region is more stable? 1 or 2? Which one is more stable? 1. Is everyone okay? Saja, Sara, Shahama. Or should I repeat? Shahama and Sara. So here, atomic mass 50 to 60. Atomic mass 50 to 60 is more stable than any other. Okay. Uh, Nuclei with intermediate atomic mass between 50 to 60 have greatest BE over A. So binding energy per nucleon. So this is the most stable nucleus. And generally, nuclei is unstable when the atomic mass is greater than 83. Greater than 83, they are unstable. Or when N over P ratio is greater than 1, it is unstable. Or B over A is low, it's unstable. So remember, it says generally, okay? Not always. The general case is true. Not always. Then we have two type of nuclear reaction. One is nuclear fission and the other one is nuclear fusion. So nuclear fusion is, now we have this graph. So now we know the B E over A with atomic mass. When two small nuclei, when two small nuclei combine, when two small nuclei combine, they make a larger nuclei. And what can you tell about this larger nuclei? So this small one is over here, and this is over here, and the larger one is over here. So what can you tell about the larger one? Is it stable or unstable compared to 1 and 2? The third one, is it stable or unstable? It is stable because over here, because it is going towards this region, right? It's moving towards that region, so it's stable. And when these two small nuclei combine, when these two nuclei combine, they will release energy. They will release energy. Got that point? So this reaction we call as nuclear fusion. This is nuclear fusion. Similar size small nuclei combine to form a larger nuclei. And here, there's one more reaction that can happen. We have a larger nuclei. It splits into two small similar nuclei. What can you tell about this reaction? During this reaction, is energy released or energy absorbed? Again, initially it was somewhere over here, and now it has moved towards this region, or its BE over A has increased. Therefore, actually it has got much stable. That means it has released energy. So here it's releasing energy by splitting into two or more smaller nuclei, and we call this as nuclear fission. Are you all clear with the idea of nuclear fusion and nuclear fission? Saja and Taiba? Clear with the idea of nuclear fission and nuclear fusion. So in both these reactions, energy is released. So nuclear fission is when two small nuclei combine to make a large nuclei, and nuclear fission is when a larger nuclei splits into smaller nuclei, but both of them release energy. So first, let's look at nuclear fission. So in nuclear fission means it has to split. It has to split into two. So here, in the decay process, in which an unstable nuclei split into two or more fragments of comparable mass. Okay, that is nuclear fission, as we discussed. So here we have a uranium nucleus, a uranium nucleus. So let's see what is the reaction that is going to happen. 1 minute. Okay, so let's look at a uranium atom, uranium nucleus. Let's see what's the reaction that will happen here. So uranium, it's a large nuclei. Uranium has atomic mass of 235. Uranium 235, and its atomic number is 92. Its atomic number is 92. Now, what we do is, for this uranium, we are going to attack it with a neutron, a fast-moving neutron. So we know that neutron, it has zero charge, but it has a mass. Okay? When this is attacked, what happens is its mass increases. Its mass increases. So this becomes uranium 92 236. So now, due to this additional neutron, it becomes excited. Now it is ready to split. Due to this additional one electron, it is ready to split. This is split into, there are number of reactions that can happen. And let's consider one reaction. This can split into barium. It can split into barium. So the atomic number of barium is 56 and the mass number is 141. And it can split, so it has to split into two, right? It's two or more. So here it is split into two. And the other one is krypton. Krypton, it's 36. It's split into krypton, it's 36. And its atomic mass is 92. So if we look, the mass, this is 92 and 56, 36. So 56 plus 36, that is 12, 1, 92. So the atomic number is now balanced. And now let's look at the mass. 236, and here it's 141 and 92. Sorry, 141 and 92. 3, 3, 2. 233 from, if we deduct 233 from 236, we get 3. So what happens is, another additional 3 neutrons are released. During this, energy is also released. During this, energy is also released. So look, by adding one fast-moving electron, we activated this uranium, and it undergoes nuclear. This is fusion or fission. This is nuclear fission. Okay, it undergoes nuclear fission and produces barium and krypton. So there are a lot of possible reactions. Here we are considering barium and krypton. And then it also produces 3 more neutrons. So this neutron, it can attack another uranium, right? This one can attack another uranium. And again, this same reaction can occur. So here, one neutron, we attack using only one neutron. But now we have 3 neutrons. So how many reactions can it start? It can start another 3 reactions. And from that 3 reaction, it will start another 9 reaction. And so on, the number of reactions will increase. Okay. So we call that type of reaction as a chain reaction. You started one, but it is going to continue until all the uranium undergoes nuclear fission. Is that idea clear? Sarah and Taiba, clear? Or have any doubts? Sarah, how about you? So look, there are a large number of reactions are feasible. The above is one of such reactions. So there are a lot of reactions that can occur. This is only one example. So in this above reaction, around 200 mega electron volt energy is released for each fission. So every time a uranium nucleus splits into two, it is releasing this amount of energy, which is really huge. If one neutron is produced by the first fission reaction, hits a second uranium nucleus. So we are talking about this neutron, okay? We're talking about the second neutron. If one of the neutron is produced by the first fission reaction, hits a second uranium nucleus, the latter will also split. The process is continued. This is called chain reaction. So in electricity generation, we have a controlled chain reaction, that is in nuclear reactors. So what we do in nuclear reactors is, if the number of neutrons keep on increasing, it might be dangerous, right? So what we do is, we somehow absorb the energy of these neutrons, okay, by putting other atoms or by using suitable material. We absorb the energy from this neutron and let only one of the neutron continue the reaction. So if one of the neutron continues the reaction also, there will be a chain reaction, right? You started with one and it is continuing. And we every time try to control the number of neutrons produced. We cannot control the number of neutrons produced, but we can control how the reaction continues by somehow absorbing the energy of this neutron. Is that idea clear? What's happening in a nuclear reactor? And then the nuclear bomb or the atomic bomb. In atomic bomb, we do not have such a control on the chain reaction. So atomic bomb is an example for uncontrolled chain reaction. It will continue forever until all the new uranium is used. So a huge amount of energy is released in a very short period of time. Is everyone clear with the nuclear fission and the idea followed by it? And Taiba? Okay. Okay. Next, let us look at nuclear fusion. So nuclear fusion, what we do when two light nuclei are united or fused together to form a heavy nuclei, this process is called nuclear fusion. For example, we have a hydrogen nuclei and another hydrogen nuclei. We combine them to produce, sorry, this is a proton. This is a proton. This is a proton. Both protons are combined to produce the hydrogen nuclei. Okay. During that, one beta decay occurs and energy of 0.4 mega electron volt is released. So I'll explain that. So this is a proton and this is another proton. When both the protons are combined, here, what do we have? This is the hydrogen nucleus. So in the hydrogen nucleus, we have one proton and one neutron, right? We have one proton, comma, one neutron. So to convert, for one proton to convert into one neutron, an electron that is present in the nucleus or present within this proton has to leave. Okay. Remember, I'm not talking about the electron in this atomic orbital. Okay. I'm talking about the electron that is present within this proton. So in radioactivity, I mentioned that. Then one proton to convert into neutron, it will release that electron present within it. And for the conservation of energy and conservation of momentum, it releases a particle called antineutrino also. So here there is the reaction we have wrote. One proton combined with another proton, it produces the hydrogen nucleus, releases an electron. So this electron can be shown using symbol like this also, beta decay, and antineutrino as well as energy. So this releases 0.4 mega electron volt. Okay. If you all didn't get the idea of this equation, that may be due to you have not completed the video. You have not watched the recording. If you check radioactivity, then you will understand this equation. Okay. So if you didn't get it now, those who didn't watch the video, make sure you check that video and come back to this. So to carry out fusion reaction, the temperature should be in the order of 10 to the power 4. So for us to carry out fusion reaction, we need a lot of heat or a lot of temperature. Okay. And in the sun, there is that amount of temperature, right? So the source of energy of a sun is nuclear fusion. So in sun, there, let's look how it produces energy. We have a proton and another proton. Both of them combine. So proton and a proton combine. During that, it will release a beta particle. 1 minute. Here, sorry, in this equation, it is not beta minus, it is beta plus. Okay, so this will be not anti-neutrino, this will be neutrino, because proton has to become a neutron. So it has to release the positive charge in it. Okay, so it releases the positive charge in it, then it releases 0 and +1. During that, it releases a neutrino. Okay, so here, are you all okay with this equation? Is everyone okay with this equation? Or any problem with that? About this beta plus decay and this neutrino? So the idea is like I just simply tell. Now we think that proton is not divisible, right? But actually proton is made up of something called quarks. So those quarks have charges. Okay. So these quarks, in addition to quarks, there are leptons and all that we will be discussing. So inside this proton, actually there's an electron also. Okay, there's an electron as well as there is something called a positron. So that is a positive electron, opposite to electron. Okay, if this proton wants to convert into neutron, it can release this positive positron. Okay, if it releases that positive positron, then it will become neutral, right? For conservation of energy, we need something called antineutrino. That's all is the idea. Is this idea clear? Those who couldn't watch the video, Saja and Sarah. If a proton wants to convert into neutron, it will release the electron or the positron within itself. Okay. Inside this proton, there is something called positron. It is released. Then that positive charge becomes neutral. Sarah, okay. So here also, we have two protons. This is a proton, this is another proton. And when proton and proton combines, this is forming the hydrogen nucleus. So we know in the nucleus, there is one proton and one neutron, right? So let's say this proton didn't undergo any change, but this proton has converted into neutron. So during that, it will release a positron. Okay, we can show positron by beta +1 also. And during that, it will release a neutrino. Okay, Sarah and Saja. Now let's look how the sun produces the heat energy. So we have this proton and another proton. Both of them combine. When both of them combine, it will release a positron. It will release a positron, and as well as it is going to release energy, right? It will release energy because both of them are undergoing fusion, and it will also produce the hydrogen nucleus. Okay, and with this hydrogen nucleus, another another proton will combine. With this hydrogen nucleus, another proton will combine, and when this combine, so here also it is undergoing a fusion, right? This is also a fusion. So during fusion, it will release energy. It will release energy, and in addition to that, now to this hydrogen nucleus, if one more proton gets added, it becomes helium. It becomes helium, right? So this helium, a similar process is occurring down here also. And then these two, helium nucleus. So now the helium nucleus is a bit large. So this helium nucleus, it undergoes fusion. So when this helium undergoes fusion, now it produces helium 2,4 nuclide. And again, because this is fusion, it will release energy. At the same time, it is going to release a proton. Plus energy. Okay, so look, in the sun, hydrogen is converted into helium, and during this conversion process, energy is released. So we call this, we started with proton, and at the end also we are obtaining proton. So we call this as proton-proton cycle. Here we will be getting neutrino because that's beta emission. There is a neutrino also. Is this reaction clear? You don't need to memorize, you have to just understand. Now tell me the feedback. Do you understand how energy is released and how this proton is converted, or this hydrogen is converted into helium? Is that process clear? Do you have any doubt in between? Saja and Sarah, how about you? You need to sometimes you all might need to go through if you are not clear with the radiation, because this beta emission sometimes it might be a bit confusing if you all couldn't have watched it. So later, if you're not clear, just go through this cycle. Okay, it's not that hard. Yeah, it's simple. So this is the net reaction. 4 protons produce uh, the helium nucleus. During that, there is 2 beta plus emission with 2 neutrino and releases this amount of energy. So as a summary, what we have to understand is during nuclear fission, heavy nuclei splits into 2 and releases energy. During nuclear fission, 2 small nuclei fuse to produce a heavy nuclei. During that, also it releases energy. So, why are they releasing energy? It can be explained using the binding energy per nucleon versus atomic mass graph. So here, over here, it is the most stable. So nuclear fission happens in this direction, and nuclear fusion happens here, and nuclear fission happens here. So it is clear that it is becoming more stable. Okay. So if they ask you all to find the binding energy or binding energy per nucleon, what you have to do, you have to find what are the constituent. For example, let's say 2 proton, 2 neutron. Then you can calculate the weight in AMU. And after that, the resulting element or resulting nuclei, you can find the AMU, mass in AMU. Next, you will get the difference, which will give you the mass defect. When you multiply the mass defect by 931.5 mega electron volt, you will get the amount of energy, amount of binding energy. If you divide it by the atomic mass, you will get the binding energy per atomic mass, binding energy per nucleon. Okay. So that is the summary of this